Hi, welcome to Organic Chemistry 1. In this video, we are going to show you how to calculate relative energies of stereoisomers of Decalins, a 10-carbon 2-ring molecule. There are two main types of interactions to consider while calculating relative energies. The first is a gauche interaction. These occur between substituents on adjacent carbons. A gauche interaction is a steric interaction, which have to do with van der Waals repulsions and result when two atoms or substituents are too close together, causing strain. In this example, the gauche interaction is between the bromine and methyl groups and can be visualized by the groups being next to each other in a Newman projection. The second type of interaction is a 1,3 diaxial interaction. These are a subset of gauche interactions, so they are also due to steric strain. These occur between groups that are two carbon-carbon bonds apart. As the name suggests, they can only occur between axial groups. They wouldn't work between groups on adjacent carbons, since one group would be axial up and the other axial down. In this example, the 1,3 diaxial interaction occurs between the methyl substituent and the axial hydrogen 2 carbons away. This methyl hydrogen diaxial interaction holds 0.9 kcal per mole of energy. One thing to note is that a methyl hydrogen 1,3 diaxial interaction is basically the same thing as a methyl-methyl gauche interaction, and that's why they have the same energy. This can kind of be visualized by the Newman projection. This is also the case for methyl-bromine gauche and bromine-hydrogen diaxial interactions. Each time you have one of these interactions, you increase the strain and relative energy of that particular conformation. One molecule can have many different energies depending on the conformation. Now let's look at these two interactions in a decalin. Let's start with an unsubstituted cis decalin in which there are no substituents but rings that act as substituents. Let's first focus on the left ring. This methyl group is part of the second ring but counts as substituent. Counting 2 carbons away, the methyl will have 1,3 diaxial interactions with the hydrogens on these carbons, each 1.3 kcal per mole. There are no more substituents on the first ring, so we will move on to the second ring. This methyl group will have 1,3 diaxial interactions with these hydrogens 2 carbons away. However, we already counted for one of these interactions the first time. Even though in the first case one of the groups was a methyl and the other counted as a hydrogen, and now their roles are switched, the energy value attributed to this interaction considers the methyl group the hydrogen is attached to. So in total, we have 2.7 kcal per mole. One thing to keep in mind while looking at cis decalins is perspective. Groups axial to the first ring will be equatorial to the second ring and vice versa, so keep this in mind while looking for diaxial interactions. Next, let's look at a transdecalin where one bridgehead hydrogen is axial and the other is equatorial. If you build this with your molecular modeling kit, you will see the molecule is a lot flatter. There are no axial substituents, so no 1,3 diaxial interactions and no gauche interactions either, so we have a total of 0 kcal per mole. Now, let's make things interesting and add some substituents. Here we have a cis decalin with a methyl and a bromine substituent. First, we can count the 3 methyl hydrogen diaxial interactions from the example of unsubstituted decalin, since we know none of these groups have changed. Next, let's look at interactions from the bromine substituent group. Checking for gauche interactions on groups 1 carbon away, there are none on the left but 1 methyl on the right. You can visualize this gauche interaction with a Newman projection. Since this bromine is equatorial, there will be no diaxial interactions. Moving on to the methyl group, we check 1 carbon away for gauche interactions. There are only hydrogens, so no gauche interactions. Since this methyl is axial, we must check for diaxial interactions from groups on carbons 2 carbons away. There are 2 additional methyl hydrogen diaxial interactions, giving this conformation a total of 4.75 kcal per mole of energy. Cis decalins can undergo chair flips where the equatorial bridgehead hydrogen will become axial and vice versa. Looking at this chair flip, there's a bromine here instead of a hydrogen, so there will be different interactions than those that we had when we had an unsubstituted decalin. First, let's check for gauche interactions and look at this methyl group from the bottom ring. Checking 1 carbon away, there's a group on the left, but it's part of the same ring so we don't count it. This methyl group is also axial, so we check for 1,3 diaxial interactions 2 carbons away. There is a 1,3 diaxial interaction with bromine and 1 with hydrogen, giving 2 methyl-bromine diaxial interactions. Now shifting our focus to the top ring and looking at this axial methyl substituent, since bromine is connected to this group, we'll treat bromine as part of the group. Looking 1 carbon away, there is a group on the right that could give a gauche interaction, but it's part of the same ring, so we won't count it. Now checking for 1,3 diaxial interactions, there's a hydrogen at the top that will essentially give a methyl-bromine diaxial interaction. We check the hydrogen on the right, but we've already counted it. Now, let's check bromine on its own. We already counted the right side interactions when we were looking at the ring substituent. In the other direction, there are no substituents 1 carbon away, so no gauche interactions. but there is a 1,3 hydrogen bromine diaxyl interaction 2 carbons away. Finally, looking at this equatorial methyl group, there are no substituents 1 carbon away, so there are no gauche interactions, and it is equatorial, so there are no 1,3 diaxyl interactions. In total, we have 6.35 kcals per mole. Time for a challenge problem. Here we have a trans Decalin with many substituents. This may look complicated, but we can actually figure this out in only 2 steps. Diaxyl interactions can only happen with axial groups, so let's first focus on those. We have 12 1,3 diaxyl interactions total, 8 are methyl hydrogen and 4 methyl-methyl. Now let's look for gauche interactions between groups on adjacent carbons. To speed up the process, we can draw a generalized Newman projection. You can see that if one group is axial and one group is equatorial, this will result in a gauche interaction. So we have 6 methylbromine gauche interactions. You may be tempted to count the adjacent methyl groups on the very right and the very left of the Decalin, but these groups are actually anti to each other and don't contribute an interaction. Now, just a quick recap of everything we have covered. You should use what you already know and count the interactions from unsubstituted Decalin if the groups have not changed. For each new substituent, check for gauche interactions 1 carbon away and 1,3 diaxyl interactions 2 carbons away. While checking, keep in mind redundancy and double counting interactions, or if the groups are on the same ring and therefore shouldn't be counted. Finally, on cis Decalins, make sure you do a chair flip since the relative energy of the chair flip may be different. Now that you know how to calculate the relative energies of Decalins, you may still be wondering, why are there so many cats in this video? The answer is, why not? Thanks for watching!